And now we are considering two varieties here. So I'm defining here the regular map between them. So we are considering V and W are two varieties. And a map between them is called a regular one if they are some polynomial maps such that our phi can be written as just in a polynomial. And I mean, in each coordinate you will have just a polynomial, right? So for example, as we can see some example. So P is any let's suppose at this moment some variety, and which we can say that is T square T cube. Actually, it is defined in this way, right? And then we can define a map from B to K, which is just from K to B. The first thing is that you need to take one coordinate here, right? And you need to put here two coordinates because B is in our K square, right? So this means that we have to put here two polynomials such that the image will be here. So if you look the B, then definitely T squared and T cubed, right? So this is an example which says that this one is a regular map, right? And the regular function on B is just a regular map from B to K, right? So if you will just restrict that W is just a K over K field, then this one is called a regular function on B. And all is the collection, if I will collect all regular functions on B, that is called the coordinate ring of B, right? And it has more algebraic structure, which is called the K algebra. And furthermore, we have seen that this can be written in this way. I mean, this one is nothing just a quotient ring where we have quotient out this polynomial ring with the ideal of variety. Okay, now then we have a regular map. Okay, this is another remark which we have seen that a regular map is always a continuous with respect to topological, with respect to the discrete topology. And then we have seen that this, I'm sorry, I didn't say about this property which I have written here, but definitely I will talk about that one when I will describe the projective varieties. So I will cover this part there because that is still true for the projective varieties. So we have, if we have two regular maps, and if there is a Zariski subset on which these two maps coincide, I mean they are equal on the Zariski set subset of V, then they are actually equal on whole V. So actually you just need to see that if there is some Zariski set on which two regular maps are same, then definitely they will be same on whole V. So here is another thing which we have seen that if you are given a regular map, and if you are given a regular function, which is a regular function, which is a regular map, and but this regular function is from W to K. So this means that for each F, which means that each regular function, we can have this map, which is just a composition from a composition of phi and F, which gives you a map from K to K, which means that other regular function is defined as B. So that's why this composition gives you another regular function on B. Okay, now I have defined what is an isomorphism, which is usually is true for the general algebraic structure. So if you have a regular map, this is a regular map, it is called an isomorphism. If there is another regular map, it is usually the inverse of this one.
We have the one.
Is it fine now?
There is a small robotic noise with your voice. I am not sure what's the actual problem.
Okay, see fine or not. Okay, so this is the definition of an isomorphism, which gives you that a regular map is an isomorphism if there is an inverse of that map, which is again a regular one, and it's definitely the inverse of that one. Is it fine?
It's understandable, but okay.
Okay, thank you, thank you. Due to this one? I don't think so. Okay, so, we have already seen here, if you are given a phi map, which gives you another map from the coordinate ring of W to the coordinate ring of V, which is called the full back of this map, this regular map phi. And we have this result which says that if you have an isomorphism here, then definitely there will be an isomorphism between the coordinate ring. So if you want that, to check that the two given varieties are isomorphic or not, then you just can check their coordinate rings. If they are isomorphic, then definitely they are isomorphic as varieties, and vice versa. Okay. Okay. And the other part, here I have used that B is irreducible variety, because if B is irreducible variety, then we know that the ideal is a prime ideal, and by the definition of the coordinate ring, it becomes an integral domain. So whenever you have an integral domain, you have a very nice extension of that one. You can make this one into a field. I mean, you can extend your ring. You can extend your ring such that every non-zero element in that integral domain has the inverse. And that is called the field of fraction. So this is denoted by K of B again, but there are curly brackets. I think its battery is low, that's why. Okay, so field of fraction, this is general definition. I have not defined it by for just for the coordinate, but it's a general definition in algebra course you have already seen. For those who have already done the algebra course, they have seen this this part. So field of fraction is like just you are taking the fractions f over g, right? And f and g are just your element from your coordinate ring, and g must be non-zero. So you can see that it's like that you are extending z into a field of rational numbers. So these are rational functions here, actually, which we will call here in the next definition. And it is just like same as you are considering the fractions, like 2 by 3, 3 by 4. So 1 by 2 is just the inverse of 2. So that's why you are getting this fraction. Okay. Okay, please wait a little bit. Domain. So this means that your integral domain does not have any zero divisors. So this means that you have the ability to find the inverse of each non-zero element in that case, but definitely they are not necessarily to be in your integral domain, but you can extend your integral domain, which we call that one is the field of fraction. Like, so I can imagine the example of a ring of integers. So you know that every non-zero element is non-zero divisor there, but none of them has inverse in that one, unless that element is 1 or minus 1. But for example, 2, that is not invertible, right? That is not invertible. So what is the inverse of that? 2, it is 1 by 2. So definitely that is not a part of integer. So we extend our set of integers to set of rational numbers. And the element who have the inverses, they are called unit elements. Okay, so the definition, because I said that this is a field of fraction, which means that this is indeed a field. Every element in this field is invertible. Every non-zero element is invertible. Okay, and the element of this field of fractions are called rational functions on V, which means they are rational functions starting from like f over g type, right? And this is like defined on V, and their answer is in domain is range is K. right? Okay, and now we want to see that further extension which in the first part you have seen regular function, and through regular functions we have defined a morphism between two varieties. But generally, it is not always the case. I mean, sometimes you can't avoid the rational function. So I will give you a small example here, which is definitely different from the previous lecture. Okay. One of these, the invariant, which is this one, which is called the coordinate range at this moment. Right? There are a lot of other properties, but those properties we haven't discussed yet. So what we have discussed is just the coordinate range so far. Right? So if you are saying that like the dimension of the variety, so I didn't even define the dimension, so you can't check that one. So there are a lot of other invariants like dimension, right? But that is not defined here. Okay. So I will have so now let's consider our variety is this circle. So you are all familiar with this one. And there was a question, what is the motivation to define this rational function? Definitely you can see here, this rational function, when I'm writing here, this is actually not the correct way because it is not defined on whole V, because might be possible there are some points at which G is 0. Right? So we will consider all those. So we will call, so there is another definition which we will call the function is regular at some point where this is well defined. Right? And if we will collect all those points at which your function is regular one, that is called the domain of the definition of your function, rational function phi. Right? It is either in your rational function or either in your further rational maps. Okay, so for example, you have this variety, right? And if you have this one, let me just draw this one. So we have here 1, 0. And this is your y-axis, which is just x is equal to 0 line, right? So if you will, so how I'm defining my map is actually this one. I'm taking a line, taking a line which is crossing, okay, another point on this circle, right? And you just draw a line which is passing through this point and your chosen point. And we definitely cut this line which is x is equal to 0. So if you will find another point, definitely it is this one. And you can see that if you will take this point, then definitely it is here. So this is this point. So I can say that this point, if I'm taking this x, so I can define this is some phi of x. So I'm taking my map which is defined this projection, right? So you are taking the projection from this point to this line. So this means that yes,
How we will decide the point on the other point of the circle?
So for example, you are taking a point on the circle and you are joining this line with this fixed point. Just draw that one, definitely it will cut this point, this line x is equal to 0.
Yeah, but this point depending upon x.
Of course, that's why I have written here phi of x.
And this point should be different from 1, 0.
Definitely. So you can see that for this one, if I will take a line for this one which is passing through this one, then that is just the tangent of this circle. So this means that the image of this point is not on your line. So this is sort of our rational function. It is not defined on the whole circle. It's not defined on the whole variety, right? So in this case, we have this map. So that's why I have used this dotted line, which means that it is not defined on whole variety. So we can see that if you will take two coordinates here, let's call it phi at this moment. And if you will do little bit calculations here, and these are just algebraic calculations, and you will just take the point here, point satisfy this condition, and if you will cut this one here, then you can see that what will be that one. I mean, you have here, okay, let me just explain a little bit more. So this x is like xy coordinate, this is 1, 0 coordinate, and now you know that what is the line of equation, right? So you know the line of equation, and when you will get that line of equation, then just put x is equal to 0, right? So you will get that point.
Stereographic correlation.
It's like a stereographic projection. That's why I said that I'm taking the projection from this point to this line. Okay, one more thing you will notice here, this is not defined when x is equal to 1, which is this point actually. And similarly, I can also write this one in this way because they are just the same. Like 1 by 2 is same as 2 by 4. Right? So please, if you have any questions, please ask me. So you can see that this rational function is same as this rational function. Like 1 by 2 is same as 2 by 4. You can check that why this is true because if I want to check that this is true, so you just need to check like the cross product. If they are same, then definitely are the same. Similarly, like for the rational numbers. Okay, now you can see that this map is not actually regular one. But still, this is very useful for us. So that's why we need to extend the regular functions definition to the rational part. There is another reason is known as the parameterization of your variety, which we will discuss in the next lecture. And that parameterization is not depending just on the polynomial structure, that is also depending on the rational structure as well. So rational parameterization. So that's why we need up to the rational part here. Okay. So there is another map. You can see that it is very easy. You have already seen in lot of books in your study that is called the rational parameterization of your circle, if you remember, right? That is called the rational parameterization of your circle. And again, this is not defined for the whole one. So this is t squared minus 1 over t squared plus 1, 2t over t squared plus 1. Agree? So most of the people have seen this rational parameterization of a circle. But the problem is that because we are working in the complex number, so this is not defined at plus minus iota because t squared plus 1 has solution. I mean that is 0 at when t is plus minus iota. So this means that this is definitely not the regular one, right? It is rational function again. And one more thing we can see that if we will compose these two things, then definitely we will see that they are inverses to each other. So phi compose psi is identity on A and psi compose phi is identity on B. Okay, here what I have shown here, this is an isomorphism, but it's not like really isomorphism of regular math, but it is an isomorphism which we call here the birationally equivalence, right? Because these are defined through the rational math, so that's why they are called birationally equivalence. And we say that V and K are birationally equivalent. Okay, they are not isomorphic, but they are birationally equivalent. Okay, and last point, if we have a birational equivalence between two varieties, right? Let's call phi, then definitely they have the same field of fraction. I mean, they are isomorphic field of fraction. There is one technical problem you may ask here to me. Because when we are taking the composition, might be possible that is not well defined because our domains are very restricted because our domain of definition phi is not whole domain V. So how we can see that this will work? So definitely we will assume here certain condition or we will say here something like that whenever it is defined, because this is a rational map, composition is again rational map when it is defined. Whenever it is defined, then definitely it is satisfied. But there is one more condition which is called the dominant, which says that whenever your rational function is dominant, if it satisfies certain condition, which is called its image is the risky dense. Right? If that is dominant one and the other one is also dominant one, then definitely you can define this part. Okay, so if you have any question, please ask me. Because now I will move to the projective varieties. So far we have done this theory with the algebraic. Sorry, affine varieties, and now we'll see that what are the projective space first of all, and then we will define projective varieties. So whatever we have done in these two lectures, we will just recall for the projective varieties. So we'll just extend all these definitions, maps for the projective varieties. But before that, we need to understand what is actually a projective variety is. There is no question? Okay. So let me start with this projective and space. What is that one? Okay, so simply to know that what was affine space. Affine space was nothing just the n copies of your field, which is this one. And now idea is to extend that definition to a projective space. So the for projective space, what we will consider that is affine space of dimension k, n plus 1, right? And here we will remove this origin. And sometimes I will just use like 0. I'm removing 0, which means that each coordinate is 0 there. Okay, and now what I will do, I will quotient out with by this equivalence relation. And this is our projective space of dimension n over k. And what is equivalence relation is that one. So I'm saying that two elements are equivalent if and only if there is some element lambda, which is of course non-zero element of k, such that ai is equal to lambda bi for all I from 0 to n.
The element must be from K n plus 1. So
Yes, so that's why I started from A0. Right? So I have started this one from A0. So that this means that there are n plus 1 coordinates. So these two elements are equal if and only if there are some non-zero element which says that this coordinate, each coordinate is just the multiple of with some fixed point with that one. Right? For example, I will say that this 1, 1, 2 is equivalent to, I mean, if I'm considering P2, I will say that is the same as 2, 2, 4 because it's a multiple of 2. I cannot pick here lambda to be 0 because then I will be out of my space. I mean set. Because I'm already taking out the 0, I mean the origin 1. So that's why I cannot consider here k can be 0 or not. So k must be non-zero.
Yeah.
Okay, so it is clear to everyone what is the projective space. And now I can just write the coordinates of the projective space in this way. I will use here the square bracket, x square, let me just write, a square, a1 up to an, such that, because I can write every element in this coordinate form. These are called the projective coordinates of your element A, where this one belongs to kn plus 1 minus 0. So these are called homogeneous coordinates. Of a point.
Homogeneous is just a name.
Huh?
Homogeneous coordinate is just a name. Or
Of the point. Whatever the point is, uske corresponding whatever you are choosing, that are called the homogeneous coordinate of that point. I mean, because you know that the every element is just like the every element of the projective space is an equivalent class. So you can just choose the representative from that one and you will write that one in this homogeneous coordinate way. Okay. Now let's see what are the relation between the projective space and the affine space. Right? So this affine space has some connection with the projective space or not. Let's see carefully this setup. So let's assume that if I will just choose, oh, okay, this, okay, if I will just consider a point 1, 2, 3, an from this our affine space. Can I define the associate point in my projective space or not? Do you have any idea how I can take that one? So what I will choose what was the homogeneous coordinate in that case?
I can put a 0 in the place of the.
Okay, if you will place here something 0 and then you can just write this one. And do you think this will be here?
Only on the
If okay, if I put 1,
These AIs are all 0, then definitely it is not an element here. Agree? Yes, Akib is right that it is not true. So this means that what should we do?
we should place 1.
We should place here something non-zero. If I will place here something non-zero like 1. So what is that one? So this, if I will say that if I'm starting from here and I'm ending up here, this means that I have a map between Kn to this P, K, and so this means that this affine space is actually lying in this projective space. Agree? So the affine end space is a part of a projective end space. Okay, this is the first thing. So this means that, and if you will go back to this definition, if I will fix that one is just 1 here, then there is another part in which this can be 0. If I will just look the classes, so in that case, we just have either 0 or 1 because I can just choose the class in such way that if A naught is non-zero, then I can always choose a representative where A naught can be equal to 1. So every time, I'm not saying everything, I mean every coordinate you have this choice, but if you are just fixing this one, so if you are just fixing this position, so here this position can be equal to 0 or can be non-zero. But whenever it is non-zero, I can fix all the coordinates through this one. I can choose this one as a 1. So this means that I can write this set in this way. So I have two types of elements when it is 0. And when it is non-zero. So non-zero, so I can just put here 1. Okay, so this is my P and K, right? So whenever you have this thing, I know that this is nothing just the isomorphic copy of Kn. Agree?
Yeah.
But what about this one? This is also an isomorphic copy of Kn, which we have seen. No, actually no. Right? So this means that this is nothing. Just forget about this 0 coordinate here. What you will get? You will get n coordinates, and these are homogeneous coordinates with n coordinates, which means that is representing an element of the projective n minus 1 dimensional space. Agree? Because I can just see this one in this way. So this set is nothing just the projective space of dimension n minus 1 over K. So I can write my set in this way. So this is the affine space plus, I mean, something extra, which is known as the n minus 1 dimensional projective space. So this means that affine space is much bigger than your, sorry, a projective space is much bigger than your affine space. And this part is usually called the space as at infinity. Why it is called space at infinity? Let's see just in the case of when n is equal to 1. So when n is equal to 1, we can see that this is just a projective line. It is called a projective line. And this projective line is nothing just this K line, which is affine line, plus something. What is that one? If I will look here, this is nothing just this point. And this point is called point at infinity. And this is space at infinity. These are those things which we cannot realize in general. I mean, affine space can be somehow realized, but these are the points which we cannot imagine. I mean, we can imagine, but we cannot see. That's why they are called something, the space at infinity, point at infinity, or a space at infinity. For example, we can see what is this one. This is something, it's line plus there is another extra point. So if you will just imagine through this topology, when you will have a line and you are just an extra point here, which is like due to topology, all lines are meeting at that point, then it becomes a circle. So is actually the topologically, this is nothing just circle. This one. Because I can remove this point. And the other way to look at this one, if you will go back to this example, which is here. Okay, remember, if I will just forget about this point, right? I have mapped each point other than this point to this line. So this means that my circle is like a line plus 1 point. Which is actually we have seen as the projective line. So a circle is nothing just a projective line. Okay. Okay, there is another way to write this projective space, which is usually called the open cover of the projective space. So let me just write here ui is equal to from 0 to n ui, where ui's are nothing, just these sets. Why these are called open? You can easily see, and you can answer this question why they are open. A naught, A1, AN, such that AI, whenever the coordinate I you are choosing, AI is non-zero. So this is called an open cover of your projective space. Why you can easily see that all UIs are open because this condition, because its complement is saying that AI will be equal to 0. So this means that it is complement of an closed set, right? So that's why it is called open. So far you can say that I didn't say any topology, right? So definitely I will explain this one, what is the topology on that one. But let's assume at this moment they are open sets, right? And you can write your projective space as the open set, the union of open sets.
All AIs are non-zero.
No, the corresponding UI means that just AI is non-zero. And you can see that each UI is actually isomorphic to K and it's an affine space. Like here in this case. Because this is non-zero, so I can replace this one by the representative and it is 1. So that's why each UI, let me just add here this one, UI is isomorphic to Kn. So you can see that what is your affine space actually? It contains n plus 1 copies of Kn. Okay? Okay, is there any question related to the projective space?
But
Yes.
what will be the map?
What kind of map?
I and K.
This is a map.
U, I, and K. So
Yeah.
we will eliminate I column.
So if you have any question, please ask. Okay, now the question is, what is the projective variety? If you will just think about what we have defined as a projective variety of in a fine case, then you can just imagine what would be the projective variety a variety in projective case. So for example, if you just recall what was a fine variety, that was just a zero set of sub-polynomials, right? So for example, if I will think here, for example, x squared plus y, right? It's a zero set of these polynomials. And I want to see its solution in my projective space, which is two-dimensional, I mean projective plane, right? So the question is, we need to find all zeros in our projective space which satisfy this equation. Right? Agree? Okay. So now, if you want to see that, what are the solution of this projective space, which are lying there? For example, if you look here, then I can see that 1 minus 1 is a solution for that one.
It's the coordinate of P1.
Yes, they are coordinate of P1. You can see that if you will just plug in these values, 1 squared plus minus 1, it gives you 0. Just write this one as. So f at this point is 0, right? But you know that this point is same as if I will write this one in this way. Or if I will write here 2, minus 2. Because I have chosen some different representative, they are the same point. So this means that this must be also a solution of your polynomial. But if you will plug in this one, in this case, you can see that this is not equal to 0. If you will plug this one, you can see that this is not equal to 0. So this means that I cannot define in this way. Because this is not well defined. If I'm saying that someone is a solution, then the other representative is not a solution. So how we can fix this part? So this means what is the problem? Problem with our question or the problem which we have posed here? Or we need to something fix here. What do you think? Any answer from the audience? Online audience?
Yes, perhaps polynomial is not homogeneous, so we will make it to be a homogeneous polynomial.
Yes, that is the right answer. We need because this polynomial is not working, so this means that we need to modify our polynomial. For this polynomial, we cannot define what are the solutions in projective space. So that's why we have to consider here the homogeneous polynomial. I mean, for the projective varieties, we cannot work with arbitrary polynomials, but we need to work with the homogeneous polynomial. So what is a homogeneous polynomial? So a polynomial is homogeneous f in n variables and plus one variables, say that or whatever n one variables is homogeneous if each term in that polynomial has the same degree. Agree? If each term has the same degree. And here you can see that this term has degree 2, this term has degree 1. So that is the problem. And if you know, if you want to verify your homogeneous polynomial, your polynomial is homogeneous, there is another criteria which is very similar to that one. If you will just replace your coordinates in determinants with lambda, and if you just scale that one, you are getting this one is lambda is common with the degree of f times your original polynomial. If this is the case, then your polynomial is homogeneous. Right? So whenever you want to define a projective variety, we need to consider homogeneous polynomials. So that's why that's the way we can define. So now I can define my projective variety. So a projective variety B is defined as this set which contains all the elements such that fi of a up to an is equal to 0 for all I 1 to L, and fi are homogeneous polynomials where fi are homogeneous polynomials in n plus 1 variable. Okay, that is the way to do that. So, or either you can write in a similar manner like we have done in the previous case. Here I can just put here P, which means that I'm taking the zeros in projective variety, right? It's up to you. You want to write here or you don't want to write here. So if I will just forget about to write that one, just consider where we are working. So you have to be careful in that case. But you can see that if I'm writing here, all projective varieties, it might be possible you can see this one as a affine variety as well, and as well as the projective variety. Okay, so these are homogeneous, remember. Okay, so there are similar kind of questions which we have asked in the affine case, that it is possible to every time to find just a finite number of polynomials which defines your variety or not. So answer is yes, because this is two by the Hilbert basis theorem. So let me just collect all the properties which we have already seen in the affine case. So I will just rephrase them in the projective case. So if you have any question, please ask. So if something is not understandable for you. And similarly, one more thing, let me just define here that I will write those properties. We can define the ideal of some set A, which is in a projective variety, which is nothing just the collection of all polynomials such that f of A will be equal to 0 for all A belongs to A. And definitely here I'm just considering the homogeneous polynomial, not an arbitrary polynomial, right? So whatever the properties we have seen in affine case, they are all satisfied here, but with little bit with some you can say that some problem. So for very first one is that one, if you have here S, which is just the collection of homogeneous polynomials, then it is same as the ideal, which is generated by this one, which is called homogeneous ideal, right? This is the first thing. And definitely it is generated by finite many polynomials which are homogeneous. And second thing is that S1 is containing S2, then definitely the variety will be smaller than the variety of S1 will be bigger than S2. And the other one is that finite union of projective varieties is also a projective variety, and arbitrary intersection of projective varieties is also a projective variety. So I have just written these few properties which we have already seen in the previous affine case, which are still true in the projective case. Right? There is not too much difference at this moment. But there is a problem. If you will just consider your collection of polynomials, that is this one. What is this one? Just imagine, okay, whenever you need to understand what is going on in the projective variety, you don't need to worry about or have to be imagined in a projective space. Just consider this is like an affine space. So if you will just want to look the solution of these polynomials in a affine space, what? Is there just a point which is considering 0 origin? But that is not a part of our, because that is not giving any homogeneous coordinate in our case, in the projective case. So this means this is empty in Pn. If I will write here the affine space, then definitely it is non-empty. It is consisting of singleton points. But whenever you are considering the projective space, then definitely it is empty. So this is sort of called this ideal, which is maximal ideal. You can see that it is known as the irrelevant ideal. Because it is giving you nothing.
All maximal ideals are irrelevant.
All?
Maximal ideals are irrelevant.
No. If you have this one, this gives you this point. 1, 0, 0, 0. So not all maximal ideals are irrelevant. There is only one ideal which is irrelevant, that is generated by this x0. Oh, sorry, this is not a good one. Why this is not a good one?
Because it's not homogeneous.
It's not homogeneous. So let's fix that one. Can you fix that one? Okay, so let's fix that one. So those maximal ideals doesn't count here because they are not homogeneous. There is only one maximal ideal which is homogeneous. That is this one, which is irrelevant. The rest of the one are not homogeneous, right? So that's why they don't create any problem. But you can fix here what will be your corresponding answer. I mean, what is the ideal corresponding to this point? We have done. Yes. Okay, is there any answer from the audience, online audience?
If we remove x naught. X
If we remove x naught,
divided by x1, so on xn.
okay, then what?
That will be the ideal of this variety. Ideal of this variety for this point.
Okay, you are saying that this one.
Yes.
Okay, is it the right answer? So any answer from the online participants? So this is one of the answers which I have received here. So could you please check that one? Okay, so there is no answer, so answer is yes. If this is the case, because this is homogeneous one, it is clear to everyone. But if it's not maximal one, right? It is not maximal because x naught coordinate is missing. So x naught coordinate is free here. I mean, if you want to just look the solutions of this one, so definitely x1 coordinate must be 0, x2 up to xn must be 0. So there is no condition on that one. So this means that that is just free. So there is just a single one point. It could be anyone, but they are all equal one. Because they are homogeneous coordinates. Okay, you are saying that now it will begin with 0, I think. Okay, let's consider this problem in like in P1. Okay, you have just single variable, sorry, two variables at x0 and x1. So here I know that what is the maximal, which is the irrelevant ideal that is generated by x0 and x1, right? So this means that if I will just consider this ideal, and if I just want to see that what is the zero of this one, what is the answer? Just imagine this one in an affine case. So if I will just look in the affine case, then I know that this gives me the like this one. This will be 0, and here I can take any t where t is k. If I'm just considering that one is k2. Agree? So now imagine this one in the projective space coordinate. Projective plane mein, what are these coordinates? So because we know that we just see that these are the coordinates which we will get in that one, but because T here, but here we need to put one more with, yeah, we need to, sorry.
We will have multiplication because the whole line will represent a point here due to the equivalence relation.
Yes, that's why I'm just removing this one and I will just put here one. So this is nothing, just a single point here in this case. Because 0, 0 is irrelevant in our case, so that's why we'll just consider here one scale. It is clear? And in this way, we will just extend that idea. Okay, as was clear before, the finite union of projective varieties is projective variety of arbitrary intersection. Yeah, arbitrary intersection of projective varieties is projective variety. So this means that gives us the topology, which we will call the Zariski topology, similar like we have done for the affine part, right? So here we have on the projective space the Zariski topology where flow sets are projective varieties. And Kn, as I said before, Kn, if you remember, was isomorphic to U1. As I said that this is open one, so this means that the affine space is a Zariski open set in your projective space. So I can write here this Kn is Zariski open subset of Pn, right?
Kn is the open.
Sorry? Kn, yes, Zariski open set.
No.
Okay, now let's see some examples to get better understanding how to work with the projective varieties. Okay, so for example, if I'm taking my projective variety as this one, which is defined in this way. Okay. So omega times x is equal to y square, and you are just taking the coordinates from the projective space plane here. Okay, now I want to see that how we can see this projective variety. So the very simple idea is to see that one is affine part. So let's just consider omega is 1, like here in this case. We can see that the fine space is just a Zariski open set here. We have started with that one. So if I will just put here the omega 1, which means that this gives you actually our variety with intersection with the affine. So this is a fine part of this variety, right? But it is important which affine copy you are testing. It is very important here. Right? For example, I'm here taking the first coordinate 1. If you will take the second coordinate 1, then definitely it is also gives you the affine part of that variety, but in different coordinates. So in each coordinate, you have different answer. Right? So you can here just start with one of them. And if I will go with that one, then I can see that this is nothing just an affine variety. Right? And in this case, it is just equal to these xy coordinates now, because I can just map one xy with xy, such that it satisfies the same condition, x is equal to y square. And you know that what is that one? This is nothing, just a parabola. So with this parabola, okay, now we can see that, okay, this is our parabola. Now you can ask what is the part which is in your affine, projective line, because P2, if you remember, P2 is just affine space union affine projective line. So now we want to see that on this part, how this variety looks like. So for that one, we need to see this 0. So we are just looking B and that line, which is of course in P1. What is that one? So we just see that is just X, Y, right? Such that in P1, such that here omega is 0, so Y is square is equal to 0. So you can see that its answer is nothing, just a single point where Y coordinate is 0 and X can be just 1 here. So this is just a single point. So this means that I can write my variety as V bar, which is the affine part of that variety, union this point at infinity. So you have here parabola, it's like, yeah. So this is like, not this one. I was just checking in this direction it is drawing. So here is that one, and you can see that this is the affine picture of that one. But if you want to see that what is the projective picture of this one, which is like they are meeting at some point at infinity, which is 1, 0. Because X, Y is 0 here, so there is a point at infinity, which is I don't know where. So, but they are just joining at that point. Okay. That's great. So we have seen that how we can look the projective varieties, just looking at a fine part and then the rest of the part, so that we can see that. Okay, now let's see another example. But now we will consider the affine one. Okay, here let me just mention one thing. What we have done with this polynomial, we have just plugging the value w at 1, which is usually called the dehomogenization of a polynomial. The given polynomial, we started with a given polynomial which is homogeneous, and then we just looking at in the affine space, it's depending on which coordinate you are looking, and taking that coordinate is equal to 1, you will get another polynomial which is usually dehomogenized, because we have this operation is actually called the dehomogenized. And now what we will do, we will consider an affine variety, and then we will see that how we can extend that one in the projective space. Okay. So now we will consider our favorite example, which is the hyperbola one. So remember, this was the hyperbola. And now what we will do, so you can see that here it is not homogeneous polynomial, right? So what I will do with this polynomial, I will homogenize this one, right? So I will introduce a new variable and the missing part, because I know that this has degree 2 and I want this one also a degree 2 term. So the new variable will contribute to make this non-homogeneous polynomial into homogeneous polynomial. So this is called the homogenization. So when I will do the homogenization of this one, I will get some different variety. Of course, at this moment, this is going into 3 variables, right? Omega x, y, right? And Okay, let me just take this one in the projective space. I mean, you can just imagine I have missed one step here. I have homogenized this one and I just plug in here. Right? You can first consider you have just taken this one in K3 and then just you take in the projective plane. Right? Okay. Now let's see what is the relation between them. Now I have this variety as a projective variety and this is our affine variety. And you know that when I will look this patch, affine patch, when omega is equal to 1, I get back my affine variety. This is very clear. You can just like do in this part, in the first example, dehomogenize and you will get back here omega 1 and you will get back your affine variety. This is perfectly fine. There is no harm. But if you will consider this line at infinity part, what is that one? So the omega is equal to 0 gives you something, this one. This is 0. So this is 0 means that you have x, y is equal to 0. So either x is equal to 0 or y is equal to 0. So this gives you 2 points here. 0, 1, 0 and 0, 0, 1. Agree? So this is 0, 0, 1 and 1, 0. So this means that in this case, if I will look this as a projective variety, this is giving you the affine part same as the affine variety, plus there are 2 points. In the previous case, you got it 1 point, and here you can see that you got it 2 points. So if you will look just picture of that one, this is your hyperbola, right? And you are adding 2 points here, which one is corresponding to x-axis and the other one is corresponding to the y-axis. So you can see that I don't know how, I mean, there is 1 point and there is another point. So this is my 0, 1, 0, and this is 0, 0, 1. Right? So you are, for the projective case, it is not just the affine part, but adding 2 more points here. Okay. Now let's see another interesting example. So far, everything is going fine, but when we will do further example, then let's see what kind of problem we can have here. So far, there is no problem because everything is so far is like just a variety with some 1 point here, variety with 1 or 2 points. It seems to like us that because this has 2 components, so we need 2 points here. And that was just containing 1 component, so that's why this gives you like 1 point. Right? So it makes sense that they are the possible projectivization of this affine variety. Okay, now let's see this example, which is defined in this way. And we have already seen this one. This is cubic, twisted cubic variety. Oh, sorry, curve. These are actually the parameterization of this variety. So we can write in this way as well, or in that just as a like the affine variety is. Okay, so you can see this one, right? So this is at the start we are starting with an affine variety, and now what we will do, we will homogenize that one, and we will get a variety in our projective space. Let's do that one. So if I will do this one, I will get this thing. So I will just homogenize these 2 polynomials. Okay. And now it is in our T3. And again, the procedure what we will do is that we will look at the copy when omega is 1. So this gives you actually, we can see that simply, it will give you back this from C to, we will get again C, or we can just write here this. If this one, then omega. It is important, you need to know that which coordinate you are putting here, right? And now let's see what is this one. If we will look this one, what is that one? So this gives you all those points which satisfy this condition. If you will go here x by 0 and x squared is equal to 0. So x by is equal to 0 and x squared is equal to 0. So this means that x is equal to 0. That's it. So x is equal to 0, so you will get this thing. And this is sort of same as P1. Agree? Which is too big. So this means that on the projective part, I mean the projective part means that the space at infinity, it is giving you too big thing, which is you cannot imagine actually. So what is the problem here? Do you have any problem here? Or it is not a variety? It is a variety. There is no problem. If you will imagine you have just a curve here, and what you can imagine, you just can imagine that it must have just a single point, like point at infinity, because through the projective projective line is similar like the projective affine space plus point at infinity. So if you have a curve and if you want to projectivize that one, then you will have projective affine curve some point at infinity. But that is not the case. Okay, so when you are putting this omega is 1, so what you will get here? So you know you have started with this C bar. So if you will put here omega 1, you will get here y is equal to x here, z is equal to xy, which is the same variety as we have seen here. Right? It is clear?
Yes, ma'am.
Okay.
Yes.
Thank you. So now let's see if I will consider this variety, which is of course projective one, and you will tell me what is the difference between this one and that one.
Next one. There is one more. Xy square has 3D.
XY.
Square has 3D.
So this is not true. Okay, thank you. So if I want to look at this one with C, and this one with Y, so we will get one square. And C. Okay. This is my own calculation, so that's not. So now I'm taking this variety. I'm just adding this polynomial here. Another homogeneous polynomial.
X square.
Sorry, it is C.
WY will get square.
Yes.
Yeah, it's right. X square. What is wrong?
W.
Oh, okay, I have to remove this X square. Okay, thank you for that. Okay, now let's see this variety. What do you if I will just consider it's a fine part, and I just consider on this a fine part, what you will get here. Is it the same a fine part which from where we started, or it is different one?
I think it is different one because when w is equal to 1, y is equal to x square, and z is equal to xy, but x z is equal to y square, or x is equal to y over z square maybe.
Okay, so let's see that one. You are getting the same one or not? So I can just write in three variables, three coordinates, such that these three equations are satisfied. If you look the last, this is the problematic thing now so far. If you look this one, and
Yes.
if you look these polynomials, which makes your ideal, right? So let's just consider an ideal which is generated by this one. So this means that this polynomial, which is y squared minus xz will be a part of this one, because I can write x squared minus xz in this way, minus okay, like I have done the diagram. Right, and here I need to put y. Sorry, xz I'm getting here, and I need
Y square minus x here.
oh sorry, there is no. Okay, no adjustment. Right? Okay, now you can see that this new polynomial is actually in this ideal which is generated by these two. And we know that whenever you are adding a point from your ideal, the corresponding variety is the same one. So this means that it's not different from our starting variety, a fine variety. It is actually the same as the twisted cubic curve. Right? So that's why this is nothing just equal to C. Agree? So if you have any questions,
Yes, ma'am. Thank you.
that's great. So now let's see what is the other part of this curve. So when omega is 0, then what you will get is that one 0 x y z, and this will give you x is equal to 0, x y is equal to 0, x y is 0, and here we have, because x0 होगा तो y भी 0 हो जाएगा. Okay, so if you will like look the solution of that one, I will get x is equal to 0, y is equal to 0, and z is 3, so this is 1. So now we have this just singleton one, which we are amending at the first moment, right? So that's great. So what is the difference between these two varieties? This is much bigger than this variety. And this is also the projectization of this variety. Both are the projectization of this variety, but this one is the smallest one. Right? So this one is the smallest one. This means that whenever you are doing the homogenization, you can get some variety which might be bigger than what you were imagining. So you need to fix here something, which is that you need to not only homogenize the generators of your ideal, but you need to homogenize all the elements in your ideal. Then you will never get this kind of problem. And such a variety, which is the smallest variety, And this is called actually the smallest variety, right? Will satisfy this condition. So if you started with this one, and if you will consider a variety in which you have homogenized all the elements of your ideal, then you will get this one is the smallest projective variety, which contains actually this one.
How can we know that this variety is the smallest one?
Okay,
Is there a-
because what is this one? This is a fine part plus 1 point. This is the reason that's the smallest one. And as I said that we need to add all polynomials, all homogeneous polynomials of the ideal. So that's why you will get the smallest one. And here we didn't do that one, so that's why we have this much bigger. That is the reason.
The number of points depends on the components of the graph or the variety.
It's sort of like that, it's depending on that one, but it is because these are curves, so we are just imagining every time we are just getting 1 point corresponding to each curve.
The projective part of
Like in
the
the, like in the affine variety, we have the criteria that the containment, one component does not contain in the other component.
Yes,
Do we have similar criteria here?
yes. Because as I said that, because every theory which we have done for the ideals, that works for homogeneous ideals. So if you will start with a homogeneous ideal, which is generated by all polynomials which are homogeneous, and you will do the primary decomposition with that one, so definitely the answer is yes, and that theory will be just translated into the projective varieties. So whatever we have done in our affine case, that will be translated through homogeneous polynomial to the projective case, right? Okay,
So this is because of homogenization.
this is called,
This is because of homogenization.
this is because of homogenization.
So how we can fix it?
How we can?
Fix it.
I said that we need to add all elements of the ideal.
Okay.
In this part, we just picked those elements which are the generators. But here we have, actually we have just added 1 point and we get our result. But if you will say that you have put all the homogeneous polynomials from your ideal, you will get the same result.
But in the fine case, if we are done with the generators, we are done with the all polynomials. But
Yes, so that's why it is not a good idea if you will just homogenize the generators. So you need to homogenize all the elements of your ideal, right?
They can be very large. So
Yes, it can be large, but it gives you just the affine space will be the same, affine curve will be the same, affine variety will be the same in that case because it doesn't affect on affine part. But definitely it will reduce your projective part because you are adding more polynomials.
Like in the affine case, we have a special kind of generating set,
Yes.
which is coming from the global.
Yes, I will answer this question in tomorrow's lecture. How we can choose the good or what are the best choices for the generators. So we can do with this kind of idea without ignoring that part.
And there is question.
Yes, there is question. Okay, as I said before, as we have seen in this example, if you will go back to the example, so we just homogenized only the generators. This gives you much bigger, this is not, we are not saying that is not projective variety. This is projective variety, but it is much bigger we were expecting. So that's why we need to add more polynomials to get this one with the smaller one. But what kind of polynomials we can add in that part? So we can just add all those polynomials which are coming from the ideal. Because it will not change your affine part of that variety. So that's why here which this I have said that C double bar, we will add all homogenized polynomials which are coming from your ideal. That is the reason. Okay? That's it. Okay, as I said before, this is the smallest projective variety which contains this C. Right? So it is actually also known as the clear of this variety in projective space. Right? So this one, so let me just remark that one. The smallest projective variety containing B is the same as the clear, which makes sense because clear क्या होता है? Is the smallest closed set which contains your B. Or closed set क्या है? Just a projective variety. So that's why it makes sense. Definitely. We are taking a variety from the affine space. Affine space variety is not closed in your projective space because K is open. But here, because if it is already in projective space, then definitely it's self-closed one. But in affine, when we are considering from the affine part, then definitely it's not closed. But that's why it makes sense the closure of this variety. And we will denote this one in this way, like the closure of V. Okay. And now we have again the correspondence between the varieties, projective varieties, and the homogeneous ideals. But here is again the problem with that one. What is the ideal of the variety of your X? Where X is just a collection of all homogeneous polynomial. Or you can say that I can say here I is homogeneous ideal. So we know that in the affine case, this is not equal to that one, but it is equal to the radical one. And the same is true. So that's why I need to add here this Hilbert. It is called projective Hilbert. Null-Stellensatz theorem. Okay, it's saying that this is same as this one. But definitely, if we are considering here the projective case, then definitely we are considering this one is homogeneous ideal, and definitely the radical is also the homogeneous in that case. Okay, now in a similar manner, we can think about what kind of regular map between the projective varieties, right? So informally, we can think that because if you will just go back with the definition of a regular map, so let me just start with the projective varieties, right? So this one is M space, this one is M, right? And we want to define at this moment So if I will just think about informally at this moment, I'm taking a point here. And I'm just defining in terms of polynomials. So f0 evaluated at a, I will just call this point as a, right? And the last one is at n. The first thing that one, if I was saying that this must be here, these must be non-zero, all at the same time. And these kind of conditions we need to impose to define a regular map or a regular map, right? So this is the just informal idea of what we want to do. B underscore K of identity is not equal to 0. Yes, sorry, I didn't mention here that that is a homogeneous ideal. Definitely this I is not equal to, not containing actually, not containing this maximal irrelevant ideal. I not. Thank you for that one. We are avoiding this one. Okay, so the main idea is how we can extend this definition to the projective case. But definitely it doesn't work if we will just go in this way. So for that one, let's see an example and then we will come back to define it formally. So if you will just consider this example. There's a projective variety. You can see that because it's defined through this project homogeneous polynomial. And now we will just look at this affine part, which is nothing just this. We have already seen this one, which is parabola. So we have, if we will consider this one here, which is a regular map like this one. So I'm just asking this question: if you have such thing in a case, can we extend that one here or not? Right. So if we have this map, which is your affine one, so can we extend this map to B in our projective space to P1? That is our question. Can we extend this one or not? So we know that how we can extend from K to this one. We know that if we can just adding this coordinate in this way. And here we will just do in a similar manner this thing. Does it make sense? Right? We should just, yes, we can extend that one in this way. Right, but these are not homogeneous coordinates. Definitely we need to impose the homogenized type. So we will homogenize at this moment and we will get that this is omega x. Right? But what is the problem with this one? So I have this one. Now I have just tried to define a map from here to here, which looks like this one, but it is not well defined actually. If I will just consider 0, 0, 1, this gives me 0, 0 here, which is not a member of P1. Right? So this map is not defined. At 0, 0, 1. Right? Because it's not allowed us. Okay, can we fix this one in some form where we can find a map jumper where we can define this one at this point? Can you think? Any idea?
We can define rational merit.
Huh?
Rational merit.
Yes, at this moment this is not regular one, but of course it's a rational one because its domain is not complete. But can we fix this one or not? Can we choose some other coordinate here where this will work? So let's see. If I will start with this one, I know that omega y is equal to x squared. So if I will just multiply with this y, so what I will get? Because these are homogeneous coordinates, so I can do this one. I'm assuming that y is non-zero at this moment. And similarly, this is equal to x squared. So xy you get, and then I will assume that x is also non-zero, so what I will get x times xy. So this means that this I can write this coordinate in this way xy when x is non-zero, right? So I can write here this one as when x is non-zero. Oh, sorry, this is omega is non-zero and x is non-zero. So here I can write y is non-zero. So now you can see that this is perfectly fine, well defined at this point. But here is a problem. If I will take 1, 0, 0, then it is not defined at that point. So this means that there is no a single map. We can define the map in this way. So I have defined in this way. So let me just write this one on the board so you can properly see. So now I have
Ma'am, in the last step, it should be omega x squared in the last one. Omega x squared.
Omega x.
Omega. Yeah, omega x squared in the last one.
In the last line,
Yeah,
here, instead of x
in
squared,
first coordinate.
this is xy.
Yeah,
no, in the last line,
in the last
first coordinate, there should be omega,
omega x.
Why?
because omega x. we
Because
have
it's omega y.
This is xy.
Yeah.
This is y omega. I have replaced this one by x
Ah,
squared.
okay.
So that's why you get the same
Yeah.
one. So x is common. Now you get this one.
Okay, I was actually looking at the.
No, no, I have used this relation actually.
Okay.
I have used this relation. Okay, so you can see that I have now this map, which is defined from this one to this one. But if you look generally, this is not a regular one, but if you look locally means that in each part you can see that this is regular one. Right? So you can see one more thing, you can see that these are regular on the Zariski open sets. Because this condition is giving you the open condition. Right? So these y is defined as the regular map on its Zariski open sets. It's mean that V. So this means that we cannot go in this direct way. Right? So every time we cannot go in this direct way, so we need to modify our definition. So now we have definition. So and you will, one more thing you can see here, if you will just go, this is very well defined map, when you will go the intersection of those two open sets, you will see that you will get the same answer as we have here. Because x non-zero, y non-zero. So I think so I can write here x non-zero. Right? Because we assume that x non-zero, y non-zero, then we know that wx coordinates is same as y xy coordinates. So this means that on the intersection part, it is giving you the same result. So this is not saying that on one patch you have different answer and on the other patch you have different answer, right? Okay, so now we have this formal definition of regular math. So now we will define in this way. This is a regular one. If for each x there is a key open set of V such that the key open set and a sequence of homogeneous polynomial f1, f0, f1 up to fn in k x0 up to x and m, sorry, of same degree definitely, such that for all y belongs to u, fi of y is non-zero for all I, because this image is going into W, then definitely all coordinates must have non-zero entry. I mean, at the same time, they cannot be zero at the simultaneously. And the second thing is that this image is actually this one.
Oh, degree should be same. Degrees should be same.
Yes, degree must be same. This is also important. It is, you can, because these are homogeneous coordinates, so you need to have the degree same. If you have different degree, then definitely they will not have the same. If you will look the different representation, representative, then definitely you will have a problem. If the degree is not same.
But
You can have different, you can have your lambda with its degree 1, 2. So you will have your lambda square, so you will have a problem. Okay. Okay, now let's continue with this example again, because I have defined my definition of the regular function, regular math. So now let's go back to this example. And now let's see this psi part, which is from K to V bar, which is defined in this way. So this is the affine part, which we have already seen that one, right? And in projective coordinate, we will get this thing. And now we will homogenize them. Oh, sorry. Let's call it S. Now you can see that here degrees are different. So now I'm taking this homogenized new variable. So I need to put every coordinate a degree 2 element. So this is fine because we have already degree 2 element. Now let me fix this one because this is degree 1. So I need to put new variable with that one to make it 2. And similarly here, just 0 degrees, so I need to have here degree 2 part. So this is the homogenization of that. Okay, so in this case, in this way, actually, you can see that this is also regular math here, which we have defined. And this is also a regular math, which is, we will say psi from P1 to V, right? So, and we can see that these are actually the inverses of each other. So we have
which maps?
this map, this side, fine. Because I'm continuing with this example actually. So now you can see that these are actually the isomorphic. So these are isomorphic as a projective variety. right? So this V, where might be starting, this V is actually projectively, sorry, it is isomorphic to this projective variety, P1. Agree? Because now we have a map from P to B, and here we have a map from B to B. And the idea is the same one, we have extended the idea from the affine variety. First of all, we have just picked the homogeneous coordinate, and then we homogenize the coordinate, and we get that map. Okay. So far we are dealing with two kind of varieties, homogeneous and, affine variety and the projective variety. Now what we can do, we can just combine these two variety in a new variety which we will call the quasi-projective variety. So let me just define that definition because we have 10 minutes, so I just go with that definition actually. And see with the examples. So actually, by extending these definitions, we can cover at the same time lot of varieties, which are actually a varieties. Either it can be a affine variety or an projective variety, or something which is not affine, not projective, but that is still a variety, which is called as a quasi-projective variety. Okay? So that's more generalization of variety. So a quasi-variety, quasi-projective variety is the intersection of an open subset and a closed subset of Pn. Of course, we are talking about open closed sets in terms of Z-discrete topology. So a variety which is a union of closed and open sets, that is called the quasi-projective variety, right? And that is more generalized because every affine variety is quasi-projective variety, every projective variety is also the quasi-projective variety. So let's see examples. So if V is a projective variety, so we can see V as a V itself intersection with Pn.
It is actually the intersection of
Open subset of Pn.
both.
Both are in Pn. I mean, no, it is in Pn, but it is not really a projective variety, might be. Right? So if you have a projective variety, so every projective variety can be written as a closed set because this is a closed already here, and this is open is because every space is open in itself. So that's why this is quasi one. Oh, sorry, it is open. This is closed. Right? So that's why it becomes a product. And if you have affine variety, right? So how you will see that one? So I will see this one at the B bar because I will take the projectization of that one. Intersection is P. So this is closed in our projective space, and this is open. We have already seen this is open. So I can just consider this one as this one. So every affine variety is still a quasi-projective variety. Now let's see more examples. These are some sort of trivial, but definitely we need to discuss those one. Now let's see this one, K minus 0. What is it? It is affine one. K minus 0 is affine variety or not? It is not a fine variety because it is not coming from some collection of polynomials which gives you this one. So this is not a fine. Yes, that is the right answer, Sidra. So this is not a fine. It is projective one.
Of 0 dimension.
Yes.
Yeah, it's just a point in.
Okay, so this one is actually, if you will look, go back with the definition, this is an open set in Pn, P1. Agree?
Yes.
Because this k minus 0 is nothing, just this one, P1 minus 2 points. One point at infinity and the other one is this, the corresponding point of this one. So this one is 0, 1 and 1, 0. So because this is closed one, because every finite set here is closed, so the complement is open, so that's why it is open.
So ma'am, every projective variety is also quasi-projective variety.
Every,
Projective variety is
yes, we have shown here.
Yeah.
And every final.
We have shown here. But this is not a fine variety, but it is it is quasi, but it is actually, you can also say that
It's neither.
yes, this is a open variety, open subset of projective space, so it is not projective variety nor a fine one. ठीक है?
Quasi कैसे?
हाँ?
Quasi
quasi के लिए क्या होना जरूरी है?
intersection.
Okay, so for example, this is open. इसके intersection P के साथ ही करें. P, then P will play a role of closeness. So this one, as this part, intersection with P1. So P1 is closed and this one is open. Okay?
मैम ये लास्ट एग्जांपल में ए है क्या था?
So in this way, this one, A and, oh sorry, this is K and, sorry, my bad. It is an affine variety, so you can write here, this is second example, it says that it is affine variety. And then we have picked that player, which is the smallest projective variety. Yes, and then we have taken this Kn, because this is an open, there is that in the projective space, so its intersection we have already seen in the previous example that let's get it just a affine part of that.
So quasi-projective is bigger set.
Yes. So it contains both
Yeah.
affine and projective and something more than that, right? Sorry. Okay, I'm just going to finish with this last example. So I'm just going to, yes.
ये इसमें affine केस में क्या होगा? ठीक है, quasi projective variety में तो open और close भी होना चाहिए.
Open and close का intersection होना चाहिए.
Intersection. ये affine के केस में
This is not a fine. I'm not saying that this is a fine. अच्छा, affine के case में, if you have started with a affine variety, उसको then you will take the projectization of that one, which is the player, which we have already seen, and then you will just take the affine, उसका दोबारा component affine part ले, like omega 1 करने के बाद. This gives you back your variety. This is closed in your projective space, and this is open in your projective space. So that's why you get that, right?
Yes.
Okay. So let me complete this part with an example. If you remember, we have a hyperbola example, which we have already seen that is not, cannot be isomorphic to the affine line, if you remember that one. Right? But now what we will do in this case, we will see that is not, definitely not isomorphic with that K line, but it is actually isomorphic. No, projective one. Is this variety, which is quasi-projective variety. And now you may ask this question, what are the regular maps on the quasi-projective variety? That maps. is the same definition will work for the quasi-projective variety. You don't need to modify that one. You just need to say here that these are quasi-projective variety and this map is regular if you have these conditions. Because it's completely, perfectly fine for the quasi-projective varieties as well. Okay, so let me just conclude as I said before with that example. So let's do here. So you have this one. So here this is affine one, not projective one. But affine is also the quasi-projective, so that's why this isomorphism is as quasi-projective varieties. Right? So now we can define this map, which is this one. Agree? Because this point will be here. And this is definitely, it's not, okay. So what I will do, I will homogenize alpha because I need to discuss this one as a quasi-projective variety. So I have to translate each and everything in the projective space. So I will homogenize first of all. Oh, sorry, projectiles. And then homogenize. So when I will homogenize, then I can see that this is of degree 2. So I will get these here. This is I will get S, sorry, T, ST, and here will be S here. Okay. Agree? You just can imagine how I'm getting this one. If you will take ST common, then you will get here 1, there T, and there is 1 over T.
S common.
ST both.
Ma'am, there should be S.
You can just see it's the same as T squared 1. And now you can just go with this. So making this degree 2, definitely there is no T, so it's depending only on S. This is degree 1, so you will just multiply it. Yes. Okay. So because it is well defined, I mean, if I will just look, what is the domain of this morphism? It is whole V, whole H actually. So sorry, whole K minus 0. So it means that this is well defined one. So it is actually a regular map. Right? So phi is a regular one. Because if you will go in this way, these coordinates are just a polynomial. So that's why it is perfectly fine. And for the other map, I mean the inverse map, it is going to for a k minus 0. You can take the points x, y, and they are going to x. Because here x can never be 0. So definitely here you will never get 0 point here. And no, you can still homogenize that one. Homogenize and then projectization you can do, and what you will get here. This one. So here x is non-zero. Right? So definitely you will never get here 0, 0. Okay, so this and moreover you can see that they are inverses to each other. So this means that their age is isomorphic to k minus 0 as projective varieties. Quasi-projective varieties. Okay. And a similar manner, we can extend the definition of the rational map, but definitely that I will do in the next class and a little bit computation about the generator of the ideals. So any algebraic set in Pn is quasi-projective? Yes, answer is yes, as we have seen here. In the first example, we have considered this projective variety. So every projective variety can be written as V intersection with Pn. So V is closed in Pn and in the projective space, and Pn itself is open in itself, so that's why it's this one. What will be the variety of ideals in quasi-projective variety? Is it radical or not? So it's depending on your because here we are not saying your variety is coming through the collection of polynomials at this moment. Right? So if it is projective or affine, then definitely answer is depending on the corresponding one. But here if you will look, there is no ideal whose zero set is this one. So definitely it's not really that one. So you are, we are extending these varieties other than these depending on ideals or not. There are some certain setup, but definitely I'm not explaining those setup here. What is meant by algebraic set? It's a fine variety or a projective variety, because in some, most of the books, what I have defined as a zero set, that is called algebraic set. Either in projective setup or the affine set. Okay, any other question?
Is there any set that is not quasi-projective variety? Start from meeting ideal.
Answer is yes, because at this moment we have not defined all varieties, right? So, and there is a concept of abstract variety as well, which contains lot of stuff other than that, other than these one, which are called internally schemes. So scheme is actually a variety, but why we need to consider the schemes? Scheme is coming from like, this polynomial, this ideal. As a variety, this is giving you just a single point. But if you will consider as a scheme, this is saying that this is single point with multiplicity 2. So that scheme part giving you more information than the variety. But it also covers the construction of varieties as well. So there is more abstract way where you can extend that part as well. Okay, any question? Okay. When I said that the projectization of a affine variety, it is not necessarily to be the closure of that variety, but if you have some variety which is the smallest one, definitely clear. What does it mean a clear set in general language of homological space? And the clear set means that it is the smallest closed set which contains that set, जिसका आप clear ले रहे हो. Agree? So if you started with your affine variety, so you need to just see what will be the smallest projective variety in that case. Right? So you need to projectize that affine variety. So if that is the smallest one, then definitely it is the closure of that one. And to how you can find that the smallest projective variety or the projectization of that variety, then you need to add all polynomials, all homogenized polynomials from your ideal of the affine variety. Okay? Okay, any other question? Okay, what I will do tomorrow, in the tomorrow lecture, I will little bit continue with the rational maths and birational equivalences, just like we have done for the affine cases, and now we will do for the quasi-projective projective varieties. And then what we will do, we will little bit work on the generators of the ideals. Because in the first lecture, someone asked that the generator of the ideals are unique or not. So yes, there are some specific generators which are unique, and that is called the Grobner basis. As I have mentioned in the first lectures, all the books, Fox, Little and Chi, book, ideas, varieties, and algorithms. These all books contain that today's lectures data. And furthermore, then we will see the Grobner basis application, how we can apply those data to compute the projective variety, affine varieties, how they can help us to find the solution of projective varieties or the affine varieties, whatever the varieties are. And one more major application we will see in the next lecture, that is, can your variety has the rational parameterization or not? So we'll answer that question as well in the next lecture.